Okay, so what we're going to talk about today is rotational motion. The crazy thing about this, if you look in your books, there are essentially 2 pages of text with only 2 equations, and then there are 5 sample problems. Okay, that is packed. That is a very, very heavily packed, very dense material. Okay, if you can get 5 sample problems out of 2 pages of text and 2 equations, there's a lot there. Now, so this is on uniform circular motion and centripetal force. Well, we already know some basics about this. First of all, we know that centripetal acceleration is equal to v squared over r. We also know F equals ma. So if we're talking about a centripetal force, magnitude of the centripetal force is going to be, just substituting this in for A, m v squared over r. That seems nice and easy, doesn't it? That's easy, pure and complicated. There's a lot here. What does this all mean? First of all, we have a reflex reaction that we should say that the force is in, okay, in towards the center. So let's just take a look at a quick little basic problem here, just so we get an idea. Okay, this is like an old school playground merry-go-round. I'm going to say that the person on the outside here, it was a little circle with top view. Okay, they're going to be going around. The speed of this person is going to be 3 meters per second. The radius is going to be 1.2 meters. And we want to figure out what the acceleration is and what the force is on the person. Okay? Now the person either has to be holding on, there has to be a lot of friction, but one way or another, we know that the force on the person here has to be inward. Okay? Now, if I have to give you one other thing, that the mass, this is going to be a kid on the merry-go-round. We're going to say the mass of the kid is 30 kilograms. That's about 66 pounds. So now, our acceleration is equal to v squared over r. The acceleration is equal to 3 meters per second. Square that divided by the radius, which is 1.2 meters. Okay, and it's 9 divided by 1.2, or it's like 9 divided by 12, which would be 0.75, by 10. You get 7.5 meters per second squared. So now the force is equal to ma, 30 kilograms times 7.5, and we get 22.5 newtons. So the magnitude of the force is 22.5 newtons. And the force has to be inward at all times. Now that always causes some problems. Okay? It's hard to visualize that inward force, because when you're on that merry-go-round, you feel like you're getting thrown back. Okay? What we're talking about here is if I'm an observer looking top down on this, what force would have to exist to keep this person from sliding off? The person here is in what's called an accelerated reference frame, a non-inertial reference frame. And the forces get a little different in that situation. Okay? You can't look at things quite the same way. So there is a centripetal force that exists, which is would have to be either friction, like I said, or him holding on, that holds the child in. If you're the child on the ride, okay, you experience what's called a centrifugal force. Okay, that's the force that you feel going back. That's why you, in your reference frame, you're not accelerating. You're just there. You've got the centripetal force pulling in on you and the centrifugal force pulling out on you. But we usually look at things in terms of a rest observer. Okay, so the rest observer, looking top down, only observes the centripetal force. It's the rider that experiences the centrifugal force. And there really is no centrifugal force. It's just in that reference frame. He feels like there is one. But it's just a matter of the fact that that's actually the acceleration that the rider is experiencing. In addition, we could take a look at this. Now think about this. Okay, I'm a rider on here. I want to be 30 kilograms, that's for sure. Think about the path that's going here. If I'm out here, I'm going at 3 meters per second. If I'm over here, much closer to the middle, that's not going very fast. So if I tried to go in, okay, I'm going faster than what's here. I wind up curving out to the side. That's what's called a Coriolis force. Okay? I'm not going to get into Coriolis force, but you might have heard the term before, and I just want to kind of give you a little basic information on what a Coriolis force is. In reality, the Coriolis force, it's not a matter that there's an actual force on this, it's just that you're going faster than what you experience here. So in order to make that curved path, we model a force called the Coriolis force. Similar to the centrifugal force, it's not actually there, it's just a matter of what we use to model the situation. And it's the fact that we have an accelerated reference frame. Okay, so now, I want to take a look at a couple sample problems. I'm going to do 2 sample problems to completion, and then I'm going to start one up and let you finish it off, and you're going to show me it in class. Okay, the first one is the gravitron. Okay, I might have even talked about this last year. The gravitron is the ride that spins around. I think at Great Adventure it's called the Taz Twister. So we've got a person there in this gravitron that's spinning around. I'm going to say that the radius is of this. I'm going to use the book's numbers here, 2.1 meters. And I'm going to say that mu s is 0.4. What I want to know is how fast the rider, I want to know how fast the minimum speed that the rider has to go in order to stay stuck up against the wall without sliding down. Okay. Now, if I'm over here, okay, doing a free body diagram, it would look like this. Now, you want to draw the forces that are acting on it. Okay, and you have to be careful. Everybody always wants to say normal force points up. Think about it. Which way is perpendicular to the surface that this rider is on? Okay, in this case, the normal force is not going up. The surface is always perpendicular to the surface. The surface is like this. So what direction does the normal force have to go? Pause it. Okay. The normal force has to go inward. Gravity is acting on the rider, as always. And what's preventing the rider from sliding down? What force is it that's preventing the rider from sliding down? Pause, think. The force is the static frictional force. Okay. Now, in general, we know that if we do this, okay, well, we also have an acceleration that will point inward. So I usually, on my free body diagram, I usually like to make a note that there's an acceleration. and that's just going to be v squared over r. Okay. Acceleration is inward. So now, again, I don't attach it to the body, I just make reference to it so that I can, I have it there for my use. All right, so now, I do sum of all forces. What I'm looking for is V. So let's take a look at sum of all forces in the x. That's going to equal mass times acceleration in the x. The force acting in the x is the normal force. That has to equal mv squared over r. I don't have the normal force, so I can't solve for it yet. So let's look at the y direction. Sum of all forces in the y equals 0. We don't want this person falling down. Now, in general, we know that static friction, well, let's just do this equation first. Okay, these two forces have to be in balance, so static friction will equal mg. Okay. Now, we want to relate static friction and the normal force. In general, we know that static friction is less than or equal to μs times the normal force. But this is a case where we're looking at the point where it would just barely start moving. Okay, that's a maximum static frictional force. Okay, so we're looking at the point with the minimum v, which will give us a point where it just starts to slide. So we're maxing out the static friction. So we're going to say that in this case, in this particular case, FRS is equal to μs times the normal force. Now, the normal force is mv squared over r. FRS is mg, so I'm going to do a substitution. All right, I'm going to say mg is equal to μs times m v squared over r. My m's drop, I solve for v. I wind up with v is equal to, multiply both sides by r, divide both sides by μs, take square root, r g over us. So v is equal to, in this particular case, 2.1 meters, 9.8 meters per second squared. MUS is 0.4. Yeah, and remember mu is unitless. Take square root and you wind up with a speed of 7.17 meters per second. So now I want to take a look at one more problem to completion. This is, these problems are kind of the classic physics problems. We're going to look at an unbanked curve with friction. The next thing we're going to look at is a banked curve without friction. So here's what we have. We have a car going around a curve. Okay, we're going to look at top view. Okay, car going around a curve. We're going to say that the radius in this case is 150 meters. And US is US between the tires and the road. Now, here's the thing. You might say, well, wait a second, Mr. Phillips, this car is moving. We're not supposed to use US, we're supposed to use mu K in kinetic friction. But here's the thing. As this car goes around the bend, we're not talking about sliding. Okay? Sliding is where mu K is. What we're talking about with static friction is that they don't slide past one another. Okay? Sliding is what kinetic friction is. When we're talking about static friction, okay, the two surfaces stay in contact with one another. If you think about something when it rolls, okay, it doesn't stay, it doesn't slide past it, okay, it stays in contact with it and just rolls over top. I'll go over that in a little bit more detail in class. I don't have anything I can really do a demonstration with on the camera. But we'll get into that in class. So now, we want to know how fast a car can go around this bend without sliding out. Okay? If it starts to slide out, then you have kinetic friction. So now, I have, if I do a free body diagram, mg goes down, normal force goes up, static friction has to go in. Okay? And again, we're looking at a max situation. Okay, we're looking at the point where it goes from rolling to sliding. So we're going to say sum of all forces in the x equals mass times acceleration in the x. In this case, static friction again is acting in the x, m v squared over r. Actually, that you guys saw for the velocity, it's the same problem that we did last time. So now, in this case, and by the way, the 0.75, that's pretty standard. It can go up to about 0.8 or so between tires and road. That drops dramatically in the rain, and it drops to very little in the, it drops to much less in snow. It drops to very little in when it's icy out. So you should not feel comfortable that you can drive this speed around a bend like this at all. So anyway, FRS is equal to mv squared over r. Okay. We don't know what FRS is, so let's take a look at the y direction. Small force in the y equals 0. Normal force is equal to mg. Okay. So now, in this is different from the last one because in the last one they were flipped. This is more of the standard kind of setup that you're used to. Normal force is equal to mg. We are looking at a max situation, so we can say FRS is equal to us times Fn. So I'm just going to substitute in here. FRS is equal to us mg. So I've got us mg. Notice again that the mass dropped out. The beautiful thing about all these things is when the mass drops out, I find that amazing that it doesn't depend on mass. It's one of the beautiful problems that we deal with in physics is how often mass really doesn't matter. Obviously, in a lot of things it does matter, but how often we get mass to cancel out. And that's why I don't put numbers in early. Okay, so we're solving for v again. So now I multiply both sides by r, take square root. So v is equal to the square root of us r g. Okay, so v is equal to the square root of 0.75 r, which is 150 meters, and g, which is 9.8 meters per second squared. So in this case, v is equal to 33.2 meters per second. This is approximately, I guess 66, a quarter of it would be, talking about 75 miles an hour. Do you think the speed limit going around a 150 meter curve should be 75, or just make it a little safer, make it 70 miles an hour? Do you think 70 miles per hour would be a good speed limit? Okay, write it down in your notes. I'll check for that. I'll check for that specifically in your notes, and we'll discuss that in class on Monday. Okay. Final problem. All right, and I'm only going to do the setup on this. I don't know how many of you watch NASCAR. Probably not a whole lot. We are in New Jersey. It's not a big NASCAR area. But NASCAR probably has the best example of this situation, where on regular roads we see it, but not nearly as dramatic. If you've ever gone, most of you are driving now, if you go around a curve, most roads are slightly banked. Okay? The reason why they bank it is that it aids roads so that they don't have to depend only on friction. If you look at a NASCAR race, in the super speedways, they have by far very steeply banked tracks. It can go upwards of about 31 degrees. I think that's what Daytona is. But we're going to take a look at what a car would do going around a banking at Daytona. What the ideal banking angle would be if cars are running at full speed. We're going to say that so here's going to be our roadway. Okay, here's an angle theta. Okay, here's our car. An artist I am not. Okay, little window there. All right, and we want to take a look at the picture of this. Now, on this car here, okay, I've got two forces that are acting on it. We're going to neglect friction. This is we want to know at what angle this the banking should be, so that the car doesn't have to rely on any friction in order to stay so that the car doesn't slide out. It still depends on friction to keep propelling forward and overcome air resistance. But we're going to say we're going to eliminate the friction that's required to keep the car from sliding out of it. So now, two forces, and two forces only act on this car. So here's my car. I'm just going to make a free body diagram. I'm going to use a dot, a little bit easier to see. I've got mg that acts down on the car. And I've got the normal force that points up. Okay? And it's going to be at an angle. Now if you think about it, this angle here, okay, if this were 0, the normal force would be straight up. As this rises up, this goes to the side more. This angle and this angle are the same. So the normal force is tilted to the side, the same angle that the curve is going to be banked. Okay. Now, we know at Daytona International Speedway, the radius of curvature for most of for the two turns is 305 meters. And I know that cars will typically go about 85 meters per second. It's about 190 miles per hour. Okay, that's usually I think that's the record qualifying run. But you can easily get up to 109. Not easily. You can get up to 190 miles per hour on a regular run. So now we want to figure out. What we want to figure out is what this angle theta should be. Okay. So now take a look at this. I'm going to put in the acceleration as well. Okay. The acceleration here, and this is something that I remember as a student that always I had trouble thinking about. Is the acceleration down here because we're on a bank, or does it stay horizontal? Okay. Think about that for a second. Pause. Okay. The answer is it stays horizontal. So if I draw this free body diagram here, my acceleration is like this. That's why I didn't tilt the axes at all, because my acceleration is not on the axis, it's horizontal. So now, if I do this, I can do sum of all forces in the x okay? And in the x, okay, my acceleration is in the x. In the y direction, there is no acceleration. I want you to set up the force equations and solve for this angle theta. Okay? I want you to try to solve for the angle theta so that this car does not go down the ramp. We'll finish it off in class.